In this video, I'm going to show you how to find the first and second derivative of the function f of x equals 3x times sine x times cosine x. There are multiple ways to approach this problem, and I will try to show you all of the different ways that I can think of for finding these derivatives. Before we start, there are a few things that we need to remember to be able to tackle this problem. First and foremost, this function, f of x equals 3x times sine x times cosine x, has three different subfunctions in it, and we need to be able to take the derivatives of each of those functions. To take the derivative of 3x, we're going to need two different derivative rules. The first is that the derivative of a constant times a function is the same thing as the constant times the derivative of the function. And second, we have an x, so we need to know that the derivative of x is 1. If we forget that, we can recover that using the power rule by writing x as x to the 1 and then bringing down the power and subtracting 1 from the original power to get 1 times x to the 0, and x to the 0 is 1. Or, what I think is a little bit faster and more intuitive is to think about the graph. So if I graph the function y equals x, the derivative tells us the slope of the tangent line, but if your graph is a line, then the tangent line at any point is just that same line, and the slope of this line is 1. So the derivative of x with respect to x is 1. And then finally we have two trig functions. The derivative of sine of x with respect to x is cosine of x, and the derivative of cosine of x with respect to x is negative sine of x. Now, we are of course going to use the product rule because we have a product of functions. However, one of the things I want to show you in this video is what is sometimes called the extended product rule. So there's two ways to use the product rule to find the derivative of the function f of x. I'll show you the more traditional way first, and then I will show you the extended power rule and how we can apply it here. The standard product rule is if we take the derivative of a product of functions, we first differentiate, meaning take the derivative of the first function and leave the second function alone. And then in the second half of our derivative, we reverse it. We leave the first function alone and we differentiate, take the derivative of the second function. In order to use that approach here, we have to decide what is our first function and what is our second function. Typically, when we've seen product rule problems before this, it was a little bit more obvious because they were really just two non-constant functions being multiplied together. But here we actually have three, and so we have to decide how we want to group them. We could either group the first two functions together and call that our first function, or we could group the second two together and call that our second function, and 3x would be our first function. It does not matter. You can make it work either way. I'll just treat the first two functions together as my first function, and then the cosine x will be my second function. So now, when I apply the product rule, I start by taking the derivative of my first function, which I have chosen to be the product 3x times sine of x. Then I leave my second function alone. Then I reverse it, and I leave my first function alone, and I take the derivative of my second function. Now here's where it gets tricky. When I try to take the derivative of the first function, it itself is a product, so it needs the product rule too. So this is a nested product rule problem when approached this way. So I'll put big brackets here to make sure I leave myself enough space. And then because it's a little bit faster, I'll go ahead and take care of the derivative of cosine of x right away in the second half of my product rule. The derivative of cosine of x is negative sine of x, so I'll put that in for the second half of my first product rule, just to get it taken care of. Now, focusing back on the derivative of 3x times sine x. So now the 3x is my first function, so I'll take the derivative of my first function, then leave my second function alone, and then reverse it. 3x times the derivative of sine of x. The derivative of 3 times x, we talked about this at the beginning. The constant of 3 gets factored out, and the derivative of x with respect to x is 1. So for my first term inside the square brackets, I get 3 times 1 times sine of x, and then 3x times the derivative of sine of x, which we said earlier was cosine of x. And all of that is still multiplied by the cosine of x on the outside. And then cleaning up the other term, I have a minus and a 3, so I'll write the minus 3 out front, and then an x, and then a sine x, and another sine x. Now I could write that as sine squared of x, but I'm going to leave it for now. And then to finish the first half, I have 3 sine x plus 3x cosine x times cosine x minus 3x sine x sine x. And this is really your own personal choice, but you can distribute the cosine through if you want, and we get 3 sine x cosine x plus 3x cosine x times cosine x minus 3x sine x times sine x. Is that the simplest way to write it? No, but I'm leaving it that way deliberately because when we tackle the second derivative, this might actually be an easier way to deal with it. In fact, with what we have learned up until this point, it's the only way to deal with it. That's how you would tackle it with the sort of standard product rule. But there is such a thing as the extended product rule. What made this problem different was that it had a derivative of a function that was actually a product of 3 different functions. And the way we handled it is we grouped the first 2 together and used the product rule with that first pair being our first function and the third function being our second function, which required us to do the product rule a second time. So if I do this in general, that's always going to be the derivative of the first function times the second function plus the first function times the derivative of the second function, all times what was actually our third function, and then plus the first function times the second function times the derivative of the third function. I'm just going to rewrite it by distributing the h of x. Let's take a moment to appreciate the pattern here. So I have 3 functions, f, g, and h. In my first term, the first function gets its derivative taken. The other 2 get left alone. In the second term, the second function gets its derivative taken, and the other 2 are left alone. And in my third term, the third function gets its derivative taken, and the other 2 are left alone. It's the exact same pattern as for when you have just a pair of functions, except it's been extended to 3. And it in fact works for even more functions. So if I get a little funky with this and add a 4th function in there, I won't take you through the whole proof, but I'll tell you it's kind of exactly what you think it would be. The first term, you take the derivative of the first function, you leave the other 3 alone. In your second term, you take the derivative of the second function and you leave the other functions alone. In the third term, you leave the first and the second function alone. You take the derivative of the third, and then you leave the fourth alone. And in the final term, you leave the first 3 functions alone, and you take the derivative of the fourth function. So for any derivative of a product, no matter how many factors there are, you always take the derivative of exactly one of the factors each time. And however many factors you started with, that's how many terms you're going to end up with. So this could be a huge time saver. Let's tackle our original problem again, but this time, rather than doing the nested product rule, let's just use the extended product rule. So this time, I'm going to be able to do this very quickly. In fact, I could write this down all in one line without showing any work if I use the extended product rule. I'm still going to write out the individual steps just to make it clear what I'm doing, but I would not expect you to write out those same steps unless it was helpful to you. So because I have three functions now, in my first term, I'm going to take the derivative of the first function, leave the other two alone. In my second term, I'm going to take the derivative of my second function and leave the other two alone. And then in my third and final term, I'm leaving the first two functions alone and taking the derivative of my third function. And then I just actually take those derivatives. The derivative of 3x is 3 times 1 is 3. The derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. So I end up with the exact same answer that I had before. 3 times sine of x times cosine of x times 3x times cosine of x times cosine of x minus 3x times sine of x times sine of x. But I think that's way easier than nesting a product rule within another product rule. Okay, but what about the second derivative? What if I wanted the second derivative of this function? Well, now I'm going to use the exact same strategy the first time I show you how to do this because it doesn't require you to know anything that we haven't covered yet. Then I'll show you how you might tackle this problem later when we know just a little bit more about taking derivatives. So first of all, I have three separate terms here, and I'll take each of their derivatives separately. And notice that I am leaving the cosine x times cosine x as is, and same thing with the sine x times sine x. Yes, those are equal to cosine squared of x and sine squared of x, but we don't have the tools yet for taking the derivative of cosine squared of x or sine squared of x. Again, I'll show you how we will do that later after I show you how you can do it now, knowing only the basic derivatives, the power rule, and the product rule. Each of these terms has a product in it. The first term is really just a product of two functions because the constant function 3 can be factored out or left in. It really just depends on how you want to do it. What I'll do is I will think of my first function as 3 sine of x. So I'll take the derivative of 3 times sine of x, which is 3 times cosine of x, since the derivative of sine is cosine. Then leave the cosine alone for the second half of my product rule. Then I'll reverse it and leave the 3 times sine of x alone and multiply by the derivative of cosine of x. And the derivative of cosine of x with respect to x is negative sine of x. Then for my second term, I have 3 different functions, so I'm going to use the extended power rule here and start by taking the derivative of just the 3x and leave the cosine x times cosine x, which I'll now write as cosine squared just to save myself some space. The derivative of 3x is 3. Then for my next term, I leave the 3x and I take the derivative of one of the cosine x's and leave the other cosine x alone. So I get 3x times negative sine x times cosine of x. And then I still have to do the third term for that product, which would be 3x times cosine x times the derivative of cosine x, which is 3x times cosine x times negative sine of x. And just to help a little bit, because this is getting long, to say the least, I'm going to use some highlighting here to clarify where everything is coming from. So the derivative of 3 sine x cosine x gave us our first two terms, which ended up being our 3x cosine x plus 3 sine x times minus sine of x. Then the derivative of 3x cosine x gave us our next three terms, which ended up being plus 3 cosine x squared plus 3x times negative sine x times cosine of x plus essentially the same thing again, just in a slightly different order. And we still have one more extended product rule to do. So now we are going to differentiate 3x times sine x. I'm going to use brackets for this one just to make sure that I don't lose track of my negative sign. So assuming the negative is factored out, the derivative of 3x multiplied by sine x times sine x. So that is 3 times sine squared of x. Now we leave the 3x alone and take the derivative of the first copy of sine of x and leave the second copy of sine of x alone. So 3x cosine x sine x. And then finally leave the 3x and the first copy of sine of x alone and then take the derivative of the second sine of x, which gives me the same result, but with the factors in a slightly different order. 3x times sine of x times cosine of x. And everything from here on out is just cleanup work. So now anytime I have a product of the same trig function together, I'm going to write it as that trig function squared. So 3 cosine x becomes 3 cosine squared of x, then minus 3 sine squared of x. Then we have plus 3 cosine squared of x minus 3x sine of x cosine of x minus, same thing, 3x sine of x cosine of x. And now I have to be careful to make sure that I distribute my negative sign through my last set of brackets. So I have minus 3 sine squared of x and then minus 3x sine of x cosine of x. I'm writing the factors in a different order. And now I have like terms to combine. 3 cosine squared x plus 3 cosine squared x, that's 6 cosine squared of x. Then minus 3 sine squared of x and another minus 3 sine squared of x is minus 6 sine squared of x. And then all four of the remaining terms are the same. So I have 4 copies of negative 3 x sine x cosine x. So that becomes negative 12x sine x cosine x. And this is a perfectly good way to write your answer. But if you were thinking, oh man, Elise, I love trig identities, I would love to apply some here, you sure can. So one trig identity that you may remember is cosine squared of x minus sine squared of x is the same as cosine of 2x. And we can apply that with our first two terms. So if we factor out the 6, we get 6 times cosine squared of x minus sine squared of x, which could be rewritten as 6 cosine of 2x. You don't have to write the parentheses. It's clear what we mean, so it's up to you. And then the other trig identity that you might remember that goes with the same family of trig identities as cosine squared x minus sine squared x is that 2 times the sine of x times the cosine of x is the sine of 2x. These are called our double angle identities. And if we apply that for our third and final term, if we factor out a 6x, we're left with a 2 sine x cosine x, so we can rewrite that as 6x times the sine of 2x. So that's another way that you could write the second derivative that is a lot cleaner looking, fewer terms required. Okay, so all of that, a lot of steps, right? All of that is how you could find the second derivative of this product of 3 functions without having to use anything that we haven't learned yet. But to give you a preview of what we'll be doing soon, there is another rule for derivatives called the chain rule. And I'm not going to go into full detail of what it is and how it works in this video, but what the chain rule says is that if you have a composition of functions, like f of g of x, and you want to take its derivative, the way you do that is you take the derivative of the outside function. In this case, the outside function is the f. So you take its derivative, but you keep it evaluated at the inside function. So it was g of x on the inside, it's still g of x. Then, to account for the fact that g of x is itself a function, we multiply by g of x's derivative. So the way this is commonly said is that the derivative of a composition of functions is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. How is that useful? Well, for a quick example, if, say, I wanted to take the derivative of something like cosine of 2x, that is a composition of functions. My outside function is cosine of x. My inside function is 2x. So to take this derivative using the chain rule, I take the derivative of the outside function. The derivative of cosine is negative sine. But then I evaluate that function at the inside function. So notice that the inside was 2x, it's still 2x. That does not change. The only thing that's changed so far is the cosine became a negative sine. Then, to acknowledge that the 2x was there, I then multiply by the derivative of 2x, which is just 2. So this becomes negative 2 sine of 2x. It's a difficult rule to understand, but when you understand it, it's fairly straightforward to apply, and it can make so many things easier. So let's go back to the function f prime of x that we got at the very beginning when we were just using the product rule. We saw how to find f double prime of x, the second derivative of f, using nothing other than the product rule and the sum and difference rule. Now let's see how the combination of applying our trig identities to simplify f prime of x and the chain rule make finding the second derivative so much easier. So I've rewritten our double angle identities, and we're going to apply them like we did before. So we have a sine of x cosine of x, which we can use to replace with a sine of 2x. It's a little funky because the coefficient of 3 isn't even, but you can still factor a 2 out of a 3. It just leaves behind a 3/2. We don't typically do that because it's not a whole number, but there's no rule that says you can't. Then, to make it more obvious how I'm going to apply a trig identity for my second and third term, I'll start by factoring out a 3x and then rewriting the functions as squares. So cosine x times cosine x is cosine squared of x. Then I factored out the 3x, so the minus stays behind, and sine x times sine x is sine squared of x. And that directly matches up with my trig identity. So now, just a little bit more cleanup here, taking 2 sine of x cosine of x and replacing it with sine of 2x. I get 3/2 sine of 2x, and then applying my cosine of 2x identity, I can replace the cosine squared minus sine squared of x factor with just cosine 2x. Now, when I go to take the second derivative, I'm going to have to use the chain rule, but it's going to save me from having to do so much product rule work. So for my first term, the 3/2 gets pulled out, and I'm taking the derivative of sine of 2x. Sine of 2x is a composition of functions. So when I take its derivative using the chain rule, I take the derivative of sine, which is cosine, I evaluate it at the original inside, which is 2x, and then I multiply by the derivative of the inside function, which will just be a 2, but we'll clean that up later. Then for my second term, 3x cosine 2x, it's still a product, so I still have to do the product rule. I'll do the derivative of 3x times cosine of 2x, which is just 3 times the cosine of 2x, and then reverse it, 3x times the derivative of cosine of 2x. And now I have a composition of functions again, so I need to use the chain rule again. The derivative of cosine is negative sine. Evaluate it at the inside function, so again 2x stays 2x, and then multiply by the derivative of 2x. And now I'm ready to just evaluate my simple derivatives. Derivative of 2x is 2, and I put that in both places. And now it is purely cleanup. I have 3/2 times cosine 2x times 2, the 2 at the end that came from the derivative of 2x, and the 2 from the denominator 3/2 cancel, and I get 3 cosine of 2x plus 3 cosine of 2x. And then for my third term, I'm just going to combine the 2 and the 3 together. So 2 times 3 is 6, x sine of 2x, and then combine like terms. I have 2 copies of 3 cosine 2x. So I end up with the same answer as before, which is that the second derivative is 6 times cosine of 2x minus 6x times the sine of 2x. Now remember, we haven't actually learned the chain rule yet, so if that was overwhelming to you and confusing, don't worry about it. You could still handle this problem if it had been asked to you using the product rule the way we did the first time through, but this is a nice way to look ahead to, if nothing else, motivate why the chain rule is helpful and why knowing trig identities is helpful, because it can vastly simplify the process of finding a derivative.